Metals and Materials International Conference, organized by Materials and Metallurgical Engineering Department, National Institute of Advanced Manufacturing Technology, Ranchi. So yesterday was the first day of a conference, and we went through various gamuts of metals and materials, the translational research on those topics. We went through polymers, we went through biomaterials, we went through conventional metals, development in conventional metals, transparent aluminum, magnesium technology, and the need of magnesium in biomedical applications. So it was full of I say rich in technology and research parts. So now today we are going to continue that series, Professor Ghosh, and we are going to have the government in that series by widely followed in India and abroad. Currently, he is an emeritus scientist of the Indian National Science Academy in New Delhi. Professor Ghosh is fellow of all the 4 science and engineering academies of India. I request Professor Ghosh to start his keynote speech. Everything okay? So now we are going to have another keynote speech to add to the translational research metals and materials by Professor Indranil Manna. Let me introduce him. He obtained his Bachelor's of Engineering from Calcutta University, MTech from IIT Kanpur and PhD from IIT Kanpur. After a brief stint at Mesra, Hyderabad, he joined IIT Kanpur in November 1985 as a lecturer and rose to the position of full professor in 2003. He was in this position till he joined. Cut short? Okay, let me, he is from IIT Mesra. Let me, just small thing, just one line. His, he has significantly contributed. Okay. Yeah.
I'm tempted to take the privilege because Professor Manna is my supervisor. Yeah. It continues. And basically, I can say 3 lines about him. He has been director of CGCRI, CSR. He has been director of IIT Kanpur. Now he is Vice Chancellor of IIT Mesra, and he is President, Indian National Academy of Engineers, INAE. I think that's enough for us.
He has got many books, papers, and many more publications to his credit. Thank you, sir. Thank you, Director, sir, for giving the introduction. And now I request Manna, sir, to continue. Thank you.
It's actually a rare privilege to have the director of an institute as a former student, so I'm honestly privileged. Yeah, maybe that's good. So, very good morning. Professor Ghosh, it's a privilege also to have you around when I'm talking that too on the recent advances in manufacturing area. Professor Madhu, Professor Kapoor, Nagahan Maya, good friends, and dear students. I understand that according to Dev Das, this is the Silver Jubilee, related to the Silver Jubilee celebration of the materials and metallurgical engineering department, and of course the international conference. I think Madam was trying to explain my background, so here you see the 2 evidences. basically, I can still wear 2 or 3 hats. One of them, of course, is IIT Kharagpur. I still continue my affiliation with IIT Kharagpur, and this is my 38th year. I'm not making a mistake. This is indeed my 38th year in continuation, even though I was in various places in between on leave. Like even today, I'm on leave from IIT Kharagpur, and I happen to be heading the Village of Technology Mesra in the same city. I think the most of the students would possibly be able to recognize by me. And I would like to use this opportunity to talk about, as I said, the current directions and certainly a future sensation in terms of manufacturing possibilities. So plain and simple, the background would be the following, that the conventional way of manufacturing, essentially, one would expect large volume, large weight, huge floor area, big machines, a lot of manpower engaged in various intermediate steps. So as a result of which, you would expect that you would first start with a semi, and you have multiple stages of semi, and then eventually when you produce the product, the final 3-dimensional product with the desired specifications, you end up making so much of a material which either are waste or need to be recycled. If you do just the reverse, you start with raw materials, and then you end up with the finished component to the exact specification, and yet you produce practically no waste or no excess material, then that is what is called additive. So very well you can imagine that from this very schematic that to produce a finished component of a fixed dimension with a lot of scope of tailoring, if you can do that in one single shot, then obviously you save time, money, space, manpower, and make the product at a relatively with certain amount of advantages which are impossible in the conventional way, which goes through various stages. So you can have complete digital design or make the design entirely digitally produced. You have a lot more flexibility, precision, accuracy. You don't need all the necessary expensive tooling or intermediate processing facilities. Far more green and clean in terms of the overall approach. And you actually can literally use all possible engineering solids. You basically can start with a powder or a tape or a wire or a rod. It's not so much successful as yet with ceramic, particularly the oxide ceramics, but with metals, it started with polymer, and with metals now it's quite a reality. The most important fact is mentioned here in the red. Additive manufacturing can only compete with conventional manufacturing and score over the conventional manufacturing when you're talking about high cost and low volume products. You can't really expect additive manufacturing to compete with a simple nail or a small component compete with the conventional manufacturing in terms of products which are fairly cheap and very easy to produce. There are disadvantages as well, and one has to be realistic. The disadvantages mainly come because of the possible defects that we may incur. The whole process is essentially a droplet integration process, whether it's a polymer or a metal. So when you actually fuse 2 droplets, and if you have multiple of them joining one after another in series, there's every possibility that you trap also porosities, or during shrinkage, you may be left with certain shrinkage cavities which may turn out to be internal cracks or defects. So that's one of the major concerns. The other concern is, of course, the heterogeneity in terms of composition and microstructure, but that can certainly be very well managed within a very short length scale. So as a result, when you have segregation or variation of density over 1 millimeter, you can easily make out. But when that length scale shrinks to 1 micrometer or less, then it doesn't quite affect the overall integrity of the component. For property-wise, one may claim that this certainly is going to be better than the normal cast products, but cannot compete exactly with the rock products. So somewhere in between. So with this, I'll use this one. So this is very important, of course borrowed from the internet sources many of you would have seen, but two important points to mention here that if you look at the cost per component as a function of customization, degree of complexity and customization needed. Today you have, for example, 20 millimeter diameter and tomorrow you want 22 millimeter. Or you have a curvature of, let's say, some few degrees and you want to increase or decrease the curvature. Or you want the sheet thickness to vary from X millimeter to 1.2X millimeter over a certain span of period. So all these complexities and customization, if you wish to introduce, in conventional manufacturing you have to change the mold, you have to change the die, you have to change various tools, and altogether quite a bit of changes would be necessary. In case of additive manufacturing, the cost per component is independent of the customization or degree of complexity. Number two important fact is that whether you produce 10 or 100 or 1,000 or a million, approximately the cost per component would be the same. So that's why you are seeing a horizontal line and a line which is flat. And so you are seeing, I can't even roll the cursor. This is better? Okay, that's much better. So these are the two major advantages, right? But it is because of this reason, this is the growth curve in terms of volume of business done in billions of dollars over a period of time. And you see the history is just about, though it starts from 93, but reasonable amount of work started happening only in this millennium. So let's say, I would say that history is about 20 years, but 20 or 30 years doesn't matter, that until about 10 or 15 years ago, the total volume of the business was hardly about $1 or $2 couple of million dollars. And today we are talking about, this is old, 2018, 5 years hence, we are somewhere around already 20, and projection is that in another 5 years, just in another 5 years, it's going to cross $50 billion worldwide. So this exponential growth is enough for any manufacturer, any entrepreneur or investor to look at it, give a serious look, and then explore whether we can make use of it. So those of you who are in NIAMT associated with manufacturing, I'm sure all of you would find it very interesting to realize that the future of the manufacturing possibly will be in this. And it's not just savings accrued from the savings of the raw material, it's about flexibility and unexplored possibility, which should be the main reason as to why additive manufacturing is going to be the future direction of manufacturing. So already these are examples like Daimler or BMW, even Airbus, all these big giants who produce millions of components and who have, for a single component like an aircraft, easily will have a few tens of thousands of small components. Now, if you have to maintain a warehouse for, let's say, just a passenger bus, the total number of spares that you need to have in the store would be easily a few tens of thousands. Huge space, huge logistic challenges, and if the bus fails in Ranchi and you have to bring it from Mumbai, then there's a lot of time delay and transportation cost involved. Whereas if you have, let's say, 10 such additive manufacturing centers, so moment a component fails, the order is placed, you possibly can produce and see the replacement in matters of hours, if not, can be fairly quick, much quicker. If you look at the overall share, sector-wise share, then the industrial production and manufacturing areas, aerospace industry, automobile, motor vehicle industry, they account for nearly 60% of the total volume of business. But what is coming up is also that, for example, conventional sectors which nobody ever believed would be useful for additive manufacturing, like say construction industry. Today, big buildings actually are constructed in matters of days, certainly not months, let alone years, just because of precast structures which are produced on site and assembled. So similarly, biomedical is another area where a lot of customized components, say for example, even if two persons are of the same height and the same weight, there's no necessity that the bones and various other anatomical structures will be exactly of the same dimension. So when a surgeon wants to replace or add on something, customization becomes necessity. And that is fairly easy through additive route rather than through the conventional route. So that's also one area where, and nobody would like to, nobody would mind paying an extra amount of money when it concerns replacement of a heart valve or a very important joint and so on. The tool, there is no necessity one has to do purely only by one single tool, but the tool that I am personally devoted to is laser, and there's a very obvious reason as to why we consider laser to be a very important tool for additive manufacturing, coherent both spatially and temporally. So there's no divergence, runs in straight line, you know exactly where you are going to make it hit and produce the heat, and also in course of time, there is no variation if you can maintain the intensity constant. Monochromatic, so you know exactly what is the wavelength. So as a result, it's very easy for you to compute what's the amount of heat delivery at the given point of irradiation, area of irradiation. I already said about low divergence, and this is what attracts the manufacturing industry the most, high power density. So literally anything from a very low melting thermoplastic polymer all the way to diamond or even tungsten or high melting solids, be it metals or ceramics, or independent of the bonding characteristics. So you can melt polymers, you can evaporate metals, you can fuse oxides of very high melting temperatures. So all materials, irrespective of their origin and bonding characteristics, can be heated up to the extent that you can actually control only in terms of two process parameters. Of course, in additive manufacturing, the third angle comes. I'll come to that in a minute. But if it comes to only heating, melting, or thermal treatment, you need only two independent parameters, the power density and the interaction time, by virtue of which you actually can do only heating. You can go into the fusion zone, come back, solidify, or you can even evaporate and then deposit. So all the three states of change of states are possible by varying two independent. I can independently vary the power density depending on the amount of energy that I'm pumping in, and the interaction time. Say for example, the diameter or the area divided by the speed at which the tool is moving. So that gives you a time component. And as you can see that almost all possible stages of manufacturing is covered within this small domain. So that's the biggest advantage. The other advantage comes from the fact that if you compare with other directed energy tools, for example, ion beam or electron beam, generally they give a Gaussian profile of energy deposition, which means that the peak will be not at the surface, but below the surface, under the surface. In case of laser, the deposition profile is exponentially decaying with depth, which means the highest temperature will be at the surface, and then the temperature will gradually decrease. So I know exactly where I want to heat, and in fact, if I need a deep penetration, I can as well manage to focus my beam not on the surface, but below the surface. So as a result, I can go deeper. So all these maneuvering is possible with laser, and if it's, one other important point is that I can divide all solids primarily into two, for my convenience, into two parts, two compartments. One where the band gap is finite. So I'm talking about insulators, semiconductors with a certain finite band gap. And there you have to lift the electrons in order to energize and transfer the heat. You have to lift from the base level. Let's say I have a band gap, means I'm lifting from the valence band to the conduction band, and then further energize. And when they come back to the ground state, they transfer the absorbed energy as sensible heat. In case of metal, I have an overlapping band. So essentially electrons are available already on the conduction band. I simply energize them. So in case of metal, the heating is faster, but at the same time, the reflection also is more. So I have to know this basic physics so that I can deal with the solids and then impart exactly the amount of heat that I want to take it to the required state of only solid state heating or melting followed by solidification or evaporation followed by deposition. I'm sure as students of NIFFT, you are all quite aware of these kind of possibilities. So these are the conventional processes. I use the word equilibrium because the microstructural evolution in all these cases is time dependent. So if you allow more time, you actually come closer to the equilibrium microstructure, be it melting, casting, heat treatment, sintering, rolling, extrusion. So in all these cases, we are talking about mass production. They are relatively slow based on certain machine tools, and the microstructure or the outcome, the properties, are more or less predictable. I know what is the, for example, tensile strength, to what extent I can go. If I want to break away from that, and if I want to produce something which doesn't exist as on today, then I'll resort to so-called non-equilibrium processing. That means I'll break away from the Gibbs rule and would like to try to enter into a regime where I can produce an aggregate which is not predicted by the phase diagrams. So in that case, I can resort to one of these techniques, and this is the technique that we are concentrating on, laser material processing. So while I do that, while dealing with materials, so that means I have a source of heating and I have material. And as I said, I can have any of these three fundamental materials, polymers, metals, and ceramics. So I can use any one of them, and imagine that I'm using maybe not necessarily a single component, because you never use pure material, pure component for production. You always use alloys or various mixtures. Then I'm bound by one other, I'm basically bound by two constraints whenever I'm talking about conventional processing. One is the thermodynamic constraint, which means that if this is a binary diagram of AB, I can pack only, this is the maximum amount of B I can have in A, and this is the maximum amount of A I can have in B, right? This is the solubility limit. It's almost like, call it God-gifted or nature-gifted. You can't defy it so long you equilibrate at this temperature. And also you can't ignore the fact that if you have a liquid of any composition throughout, you can have 1% B in A or 99% B in A. Nobody stops you because you're in liquid, you have complete solubility. But as soon as you cross this horizontal line, which is an invariant transformation line, there's no other way than to allow two solids forming simultaneously. You call it eutectic transformation. So these are the restrictions or the ordains of the nature which you cannot defy altogether. And then the other constraint is the mass transport rate. Whenever you want to produce something new, for example, if this hall has to be reorganized, then individuals have to move from respective chairs to the next chair and so on and so forth. So you require mass transport. And typically in crystalline solids, under equilibrium condition, such mass transport, solute transport happens by diffusion, which is integral multiple of interatomic distances. So that is temperature dependent term. So depending on what temperature I'm dealing with, I have another constraint. So these are the two constraints that I always have to bear in mind when I'm trying to design new material or new structures or process even, new or old, doesn't matter. So in order to overcome that, I have to resort to non-equilibrium processing. So this entire gamut of additive manufacturing, this also is borrowed from the internet source, so you might have seen this before. So essentially, this is by and large captures well the entire possibility. And so this, until this part, you actually can produce Vetlich parts through indirect measures. So either you produce a mold and then you cast, or you do partial processing and then final processing, maybe you heat or sinter, or maybe you have to do final machining. And you can do not only just metals, you can use it for polymers and various other, but you certainly can produce very complex shapes like this kind of a heat exchanger and so on. But on the other hand, you also can do direct manufacturing of components by one of these techniques, which is on the right side of the view screen. From binary dating to, I would rather say that powder bed fusion and so on. But I would like to simplify saying that for the time being, if you're interested in metals, then there are two ways I can do additive manufacturing. One is the so-called fusion bed, or you call it a fixed bed, or powder bed technique. So I have a bed of powder, and like I have a bed of powder, and I have a source of heat, and let's say that source of heat is actually a very small line or a spot, and the moment it moves over or hits a point, I immediately melt and fuse, and then I move the beam. So obviously, by the time the beam is moved out, the previous point is already solidified. So likewise, I'll have droplets, or essentially small volumes of fusion regions moving linearly in direction, then in the perpendicular direction, and when I complete this entire X and Y over a given area, then I have a sheet, and when I start building vertically, then I have a three-dimensional component. So that's the idea. The biggest disadvantage of this technique is this is very good, and this is actually adopted and very routinely practiced in industry for a component where you don't want to change the composition. That means one gear you know very well of a given dimension or changing dimension, but the composition is a fix. So you have a huge powder bed, and you make use of that tank of powder for manufacturing the component. But on the other hand, if you are a little bit, we should try something different. You have the attitude of exploring something new. In that case, you might like to change the composition, you might like to change the dimension, you might like to also vary along the time you are actually feeding the powder. So there I'll have a different configuration. Instead of a tank of powder, I'll have a nozzle, which essentially is a coaxial nozzle. So through this central region, I'll have the laser beam coming through, either fed through some reflection method or through directly by a fiber. And I'll have these nozzles which are feeding the powders directly into the spot. So this is where the trick lies, that the two streams, in fact, I can have multiple feeder nozzles and feeding not necessarily the same powder, different powder. Even during feeding, I can keep changing the proportion of A, B, C, so I can vary the composition. Even in the simplest case, when I'm feeding same stainless steel from 4 different nozzles, I have to make sure that the point where the powders are converging, the laser spot should also coincide exactly at that. So there should be a total coincidence or convergence of the laser beam and the powder feeding point. So then I move along this line. So this part, already by the time the beam has moved to this part, this is solid part. By the way, I'll finish this part, then I would have moved one step ahead vertically. And that's how I'll keep moving along X, along Y, and then along Z. So that's how I produce a three-dimensional component. It can be a simple block like this. It can be a circular tube. It can be an inclined tube. It can be a nozzle with a conical shape. It can be very complex design of a component. Anything is possible. But here you have the flexibility of changing the composition or the dimension better than what you have in the powder bed system. I'm very proud to show this view graph because 1995 I had historically my first exposure to a laser lab, a full-fledged laser lab. Though I actually processed steel, somehow, I don't know how it happened, accidentally asked me to write something, and that's how I first started learning about laser. That was in 92, but 95 I was fortunate to spend a summer with Professor William Steen in Liverpool. That's when I first saw a laser lab and also was privileged to handle it myself. So since 1995 until 2018, I always dreamed of having a laser lab of my own. And since I didn't have a lab of my own, that made me go all over the places, literally all over the places, every single country, and fairly renowned laboratories in Germany, England, in US. I would have had some collaboration and would have guided some projects as students together. But in 2018, I got a very large grant from TST, thanks to them, about 6.5 crore. And so this is a complete robo-loaded fiber delivery laser system, powder delivery, powder fed system, not powder bed. This is a stage, and this has a 6-axis rotational facility. I have a powder delivery system, twin hopper, And so I can vary the composition. And the most importantly, it's a 6 kilowatt, 6-axis laser delivery system. It's a diode pumped, but delivered through a fiber. So now on to some results. Partha, you have to tell me about the time in case I overshoot.
It's up to you.
Okay, then I have the freedom. That's the advantage of having a director of the institute as a former student. So, I mean, this is the monster that all engineers would like to do something someday, somewhere, so that one can claim that I have developed a turbine blade or a disc or something to do with a coating or something like that. One of the finest example of engineering in my own understanding, because these blades that we are talking about is actually an 8 to 10 component system, single phase, and more than that, single crystal. Those who study metallurgy would know what a monstrous job that is, to be able to retain all of them in single solid solution and then develop only as a single crystal, one single orientation. But they are exposed to 1050 or above temperature, so they are prone to high temperature oxidation, creep, and several other thermal fatigue damages. So there's enough amount of research always happening to improve farther and farther, because if you can rotate at higher speed and can withstand higher temperature, your thrust to fuel ratio increases, and instead of 10 hours, you can fly continuously for maybe 20 hours or so. So obviously that's a big difference. So from this, the next ambition of humankind is, why only travel from New Delhi to New York? Why don't we go to the moon and come back after the summer vacation? So for that, you need a re-entry vehicle. And for the re-entry vehicle, the biggest threats come from these nose cone, the fin, the advancing edges of the fin, of the wings and the fins. Because these red lines, as you can see, they experience temperature in excess of 1500 or more, I mean maybe 2000 or so. So in order to protect these regions, you won't use metal unless you can afford to take, let's say, tungsten or tantalum. But density-wise, they are the worst candidate possible for any of the flying objects, very high density. So you'd like to go for things which are very lightweight and at the same time can withstand such high temperature. So you need, you will go for alumina or zirconia or one of these refractory oxides. The disadvantage is that they can withstand, they can actually fit all the bills in terms of creep, fatigue, and so on, but they are non-fusible. So you can't join, and you can't make a convoluted or a complex shape out of that because they are not really deformable. So you need tiles, and when you join tiles, the tiles at the interface may fail, and this is exactly the reason why we lost the brilliant astronaut like Kalpana Chawla. So this has been a dream of the space-faring community, that why don't we create such structures here at the leading nose cone or leading edges, which will start with a metal and end with a ceramic oxide. So now imagine you are on the cross section, you're looking at a metal base, superalloy or some such material, and you end up with the directionally solidified zirconia crystals, okay? Maybe polycrystals, but they're all directionally solidified. So if you can do that, now if you just have, imagine you have an oxide sitting on top of a metal, the interface is extremely suspect due to large expansion contraction of metals vis-a-vis that of ceramics. The moment it goes out and comes back to the, goes through a thermal cycle, the interface will give away. So instead of that, if you can have a situation where you gradually build, so you have 100% metal, and finally you have 100% ceramic, and in between you keep varying every 10%, every 20%. So obviously the coefficient of thermal expansion mismatch will be minimized, and as a result, you can get both. You can have a metallic structure for the toughness and fabricability and thermal protection from the ceramic. So one of my students, Manoj Kumar, actually we had a funding from ISRO, and all he could develop so far was to have such kind of a layered structure, varied structure. So this is completely ceramics. You do have porosities, but we don't mind having porosities because air is a poor conductor, so that also helps in reducing heat transmission across the cross section. You need a bond port and you have a substrate, metallic substrate. Now, he did show there's a lot of description about how are these phase aggregates at different composition levels. And you can see he actually used gadolinium oxide instead of alumina or CDR because this has even poorer conductivity. So basically, this is zirconia alloyed with Gd2O3, and these are the phase aggregates. This is how you measure actually the kinetics of the oxidation. Oxides won't oxidize, but this interface, there you have the transversely growing oxides. So if you look at their growth rate, that gives you an idea as to which way the interlayer is oxidizing. So I'll skip those details, that's for the, but now actually is the novelty that we wanted to propose. So this was done 20 years ago, more than 20 years ago. And this was one of the two PhDs of Jyotsna, who first showed that people always think of oxides as thermal protection. I think this was one of the first few examples where she showed that if you have intermetallic phases, if you look at this phase diagram, look at this Ti5Si3, 2130 degree incongruous melting maximum. There's no fixed melting temperature because this is over a particular composition range, but this congruous melting maximum is 2130, but that's only the temperature. The most important thing is that until room temperature, it's a single phase. So there is no phase transition. If you have anywhere else, there will be a phase transition, and hence there will be a differential changes in volumes and expansion, contraction, and so on. So what she did was to pick up a composition in the hypoeutectic zone, but because of faster cooling, these liquidus curves actually plunge, and as a result, she ended up getting a hypereutectic microstructure in a hypoeutectic composition because of non-equilibrium cooling. What is the advantage? The advantage is nearly 85% of this matrix, this microstructure, is covered by a phase which has a very high melting temperature, very low coefficient of thermal expansion, and most importantly is much stabler and oxidation resistant than many of the, leave alone metals, even many of the oxides. So rest of the 15% of the matrix were interconnected with these intermetallic phases. So as a result, if oxygen is invading into the metal and trying to oxidize, then it cannot move directly vertically downward. It has to move in a convoluted manner. So you are deferring the oxidation process. So this was very successful attempt, and learning from that, we propose that on superalloy 718, we can have silicon, aluminium, these kind of elements. When they are alloyed, then I can have a graded microstructure which will be intermittently silicide or aluminide on the top, but at the bottom I can have superalloy. So what I'm trying to say is that if you want to deposit or make a thermal barrier coating with zirconia or alumina or whatever, you first need a layer in between which will allow better, like a Koenig-Crowley or any of those multi-component cobalt alloys, which will form a bond coating or bond layer between the base substrate and the top oxide layer. Here you don't need that. Here you start with the superalloy, and then you gradually can change the composition and ends up getting a top layer which could be 80-90% of an intermediate phase, not a monolith coating, but dispersed phases, so which is even better because in terms of coherence. What is even more significant here is this interface. You see, this is completely superalloy, and this is where you're gradually changing. They grow epitaxially, near epitaxially, with a certain direction rate. And most important, there's no crack. There's absolutely no decohesion, because you're starting with a metal and you're gradually changing your composition and making it intermetallic. So these are the descriptions of what is there at the interface and how do they oxidize, which way they are better. You can just one graph here. This is 718, base 718. and this is with one of these coatings. So obviously the mass gain per unit time is much lower. That means the oxidation kinetics is retarded significantly. So I'm changing gear, going into another possibilities of application. If you look at these buckets, you know, the earth dredging buckets and so on, or these wheels, crane wheels and so on, these kind of failures are very common, and that's why you need to change them. Now imagine you're talking about a few ton weighing rope. It develops a crack. You're not going to you don't want to throw it away right away because that's very expensive. So there you go for various kinds of refurbishment, repair, and so on. Similarly, very important components like this. So here also, at this nozzle, the very design of the nozzle, if it is assembled, there are 13 different parts, which is put into a single nozzle assembly. If you can design the same thing by additive manufacturing, then it's a single component, single part, in one single manufacturing operation. So you can very well imagine that how advantageous and attractive that is. So, so in order to do this, I mean, of course, I do not have the capability of attempting to create a nozzle, but what we are doing is, I'm going to show now 4 examples from 4 of the students. All are from Pune, all of them work for Hoganas, and all of them are interested in developing components by additive manufacturing, either for refurbishing or for direct manufacturing. So the first case is this continuous casters. Now, you're pouring hot metal from 1500, 1400, around that temperature, and then you have these rolls through which they pass through and you extract heat. So you open the gate here, the turnish opens and the hot metal flows. This is where you're seeing the maximum temperature. And this is where you're also incidentally seeing the maximum corrosion, because they are covered with fluxes which are chlorides and fluorides, one of the most aggressive compounds that you can think of. So at that high temperature with such aggressive ions, just after a few hits you have to change the rolls. Each pair of the rolls costs a lot of money. So then Nikita wants to basically come up with cladding or coating and eventually a complete roll by which she can replace some of these worn out, either refurbish them or develop graded rolls of various diameters. And she basically, okay, no, I haven't come to that as yet. So before that, this was another student. He's now not a full big shot, but half big shot in ARCI Hyderabad, leading the CLP and the laser unit there. And he was one of the first few to show something very interesting metallurgically. So he deposited H13, one of the standard grades of tool steel, on H13. Now normally in H13 rolls or buckets or something, you would use a stellite coating, cobalt tungsten carbide combination. So obviously 2 different compositions, the interface is a suspect, and most importantly, the temperatures are different, and as a result of which you refurbish, but that repaired component also doesn't last too long. So he was one of those who first showed, not necessarily the cladding with this, so H13 on H13, that's the first novelty. Number 2 novelty is, if you look at just these stress strain diagrams, so this number 3 fails early, but number 4 and number 2, they are from the H13 clad on H13 roll, but showing higher tensile strength, higher yield strength, and even greater ductility range. How is that possible? And another very interesting feature for those with a metallurgical understanding would appreciate that normally when you take steel and when you cast, you end up getting mostly austenite at room temperature because of presence of carbon and stabilization effect of carbon. So here he's able to develop this clads with a microstructure like this, which is essentially all martensitic in prior austenitic grains. So the martensitic needles are actually very fine, but confined within the hyperpyrostotic grains, and as a result of which, because of the fine platelet size, not only the strength increases with little retention of retained austenite in between, his overall fabrication range or fabricability range also improves. So this, it turns out to be that actually the top layer mechanically is even better than the virgin row. So this gives a very interesting, exciting possibility. So then, borrowing from this, we said, why not we take stainless steel and end up with a superalloy? So, not necessarily a turbine blade, but there are many, many components. Let's say a heat exchanger. So, if I have a pipe or a tube, which basically is a stainless steel tube, and then I make a clad with superalloy. Now, if I do with a sharp interface, stainless steel to superalloy, the interface is amenable to cracking because of compositional mismatch. How about doing it in some graded composition, 25%, 50%, 75%, and then I have complete superalloy. Okay, so that's the idea, and this is in progress. We certainly see that cladding is easy. There's, apart from porosity, there's no quench cracks. These are the phase aggregates. We tend to avoid intermetallic phases in large volume fraction, but not altogether. So there are niobeds formed, and that's a matter of worry that if you have too high volume fraction of these niobeds, or maybe even some Laves phases, then this could lead to brittleness, which we have to avoid. So this is what Abhishek wants to do and is doing that. The next one is, this is just an anecdotal, observation. Forget about all these parts. Sandblasting, belt grinding. You know very well that metals actually reflect more than 90% of the laser incident light because of free electron cloud available onto the surface. That's not a good news because you are giving, let's say, a few kilowatts, but only 10% of that can get coupled with the stock, which is all wastage. So you would like to improve the absorptivity of laser. The standard industrial ways do surface roughening. So you do by sandblasting, and for accidentally we said, why don't we also try with belt grinding? And now whether it is sandblasting or belt grinding, a blind man can see the difference in the microstructure. So just because the surface preparation method adopted was different, the entire microstructure could also be so much different. So that taught us one lesson, that we all tend to worry only with the laser, the power density, the speed, the composition of the powder and something, ignoring altogether the surface condition of the stock on which we are cladding or depositing. So that also has a very large bearing. So this is a similar exercise with stainless steel pure. Just to tell you this part, if you look at, these are orientation imaging mapping. So you're seeing that from the top surface you see large areas, but these color codes are only to give you an impression that if you look at the length scale, you're talking about almost like few tens of micrometers of areas with no grain boundary in between. Or even if there's a boundary, that boundary is almost negligible or can be ignored. The reason is the mismatch is so little. So in other words, laser gives us an example. So on this is the top surface. When you look from the bottom, then you see directional growth. Okay, but when they grow onto the top surface, they're not immediately providing you high angle boundaries or back boundaries with large mismatch, which is a good news because if there's a large mismatch, then there's also a large difference in electrochemical potential. Stainless steel is meant for stainless activity, for corrosion resistance activity. So if you create a top surface where the boundaries actually are less than a degree or just about a degree, then formation of galvanic cell is minimized. So the corrosion damage also will be minimized. So this is what I was trying to refer to earlier on with Nikita's work. This caster rolls, she wants to try with these compositions. I'll just fast track it. She's trying to understand how do the microstructure develop along the thickness region. So this is A, the top layer. So this is one of these alloys. In fact, this is a martensitic brand from the Hoganus group. This is high nickel. So this is austenitic. and this is also a semi-martensitic variety. So she wants to try with different. The base substrate is 4140, low alloy steel. So if you start with a low alloy steel, imagine instead of a high alloy steel, if you can change all these casters with low alloy steel and then clad it with one of these clads, and still can retain or even offer better corrosion resistance, better high temperature resistance, then the company stands to gain a lot. So that's the idea. So similar efforts is done by Mangesh, and he wants to take care of these wheels, the railway wheels and pulley wheels and so on, where cracks and erosion or wear onto the surface is very common, and he wants to prevent that by having a harder coating. So this is just a signature in terms of hardness variation, and one can make it such sharp, one can also make it shallow, graded. This is what Amitav Roy is trying to do, and his work is related to, again, with two varieties, austenitic and martensitic, and he wants to clad, let's say, he wants to develop austenitic dendrites with these carbides in between, in the interdendritic spaces. So essentially create stainless steel as a base, 4140 as a base, and develop either martensitic or austenitic variety onto the surface, and so that they can be used for more wear or conditions where the threats from wear and erosion is much larger. And then finally, for earth moving equipment, Subhranshu wants to develop a similar thing, but with, this is new, he wants to not only use one of these high alloy steel clads, but also disperse tungsten carbide into them. Now normally this is different than the stellite kind of a cobalt-based tungsten carbide dispersion in terms of coherence or in terms of compatibility. And you have very nice spherical objects. So this sphericity also tells us that there is a very little solution, very little dissolution during the process itself. So they remain solid particle and they can be dispersed. The advantage here is that if you want to disperse tungsten carbide in normal metallic systems, there will be a lot of gravity segregation. With these thin clads, you can actually maintain very good uniform distribution. So this is the last example I want to share. Essentially, this is Subhrakamal wants to develop these three-dimensional components using T800. This is again a trade name of this same Laves phase dispersed high temperature clads. And so he's trying to build large thickness and large height components and then look at their variations. So in order to do that, he's again using compositional gradation. So 40 or 25, 10 means different levels of dilution, and this is as received T800. So he's mixing T800 with stainless steel and forming different clads. The interesting part here is, I mean, for example, if you look at these blue ones and the red ones, these, so the red lines show the wear resistance and the blue lines show the hardness. So you can very well imagine that the harder the surface, the degree of wearing of that is minimal. So obviously when you have pure stainless steel, like here, you have fairly high wear volume, the red line, and because the surface hardness is small. But of course, please remember that hardness is not one and the same as wear resistance. But nevertheless, there is a very direct, Archer's law tells us there is a direct correlation. So what he is trying to show is that if I mix, if I can grade appropriately, then I can change the hardness and the wear resistance also accordingly. And in order to do that, so you develop such various types of microstructure. You can very well look out that the nature of the microstructure is different, the constituents are different. And so one actually can do a complete mapping. We know solidification behavior primarily in large volume is controlled by two independent thermodynamic parameters, the thermal gradient and the growth rate. So if I plot them, then actually it is possible, even in laser processing, which is in a small volume and which is also for a very transient, which is a very transient phenomenon, even there one actually can show such microstructural mapping as when you have very high temperature gradient and so very high G over R ratio, then you end up getting such directional structures. Whereas when you have very low G by R ratio, so you are somewhere here, then you actually can gradually change from columnar to all the way to equax regions. So that means this microcircular control is also possible. So I think now I can wind up and try and conclude certain important, make certain important statements. So I firmly believe that additive manufacturing, particularly with the fusion method, say for example with laser, is a droplet integration process. You can produce three-dimensional, 1, 2, or three-dimensional components. I mean, you can produce a wire, rod, you can produce a sheet, you can produce a three-dimensional component. There's a huge growth potential, which is what we are appreciating gradually. And the field is far from being saturated. There's enough good news for the PhD students. You can do a lot of very exciting job and produce good papers. There's a lot of metallurgical aspects to be understood. Say, for example, any conventional component, we have experience or history of over several decades, if not a century of documentation. I know exactly what is the creep level, what is the fatigue level, strength level, how would it behave under these conditions and so on. Additive manufacturing components are just hitting the market, so we don't know really how will it behave after 5 years or 10 years. So there's a lot of modeling and a lot of experimental jobs to be done in that. For example, in terms of fatigue, creep, or reliability, failure modes, and so on and so forth. So we need also a lot of good manpower. So I think the PhD students can do wonders there. So I personally see there's huge opportunity, a lot of hurdles exist, which we have to understand, and for that we need a very serious effort. And this is no longer this is no longer just a possibility, but a reality is borne by this company, Skyroot, spun off by two very courageous IIT alumni. And in fact, Kiran, who works for this company, I know him for a long time, they say that they actually are supplying maybe 20-25 components to ISRO regularly, and ISRO wants more from them. So it's actually a reality. Thank you very much.
Is there any question from anyone?
Questions?
Yes, Prof.
Thank you, I learned a lot. I was curious about one plot where you showed the cost per AM part staying horizontal. But how is that possible? Because it takes more time or more machines.
No, this is the advantage. Your design philosophy, whatever you develop in your CAD file, all flexibilities you can do in your CAD file. So today you have a dimension, let's say XYZ. Tomorrow you want X, 0.9X, 1.1Y or something like that. Your design board develops that and trains the laser beam to move exactly to that direction. So if I move from one design to another, in case of conventional places, you need to change the die, you need to change the various other things needed to.
But if you make the same part, I thought this was about the same part.
Oh, if you make the same part, then conventional manufacturing is profitable if you produce more than certain number. Yeah. Exactly. So in fact, that's what I showed. If I may just quickly go to that. So this is what you were referring to. So if you, for example, if you produce, let's say 10 parts or 10,000 parts, in case of additive manufacturing, cost per component will not vary or marginally vary. Because you have made a design, I'm saying per part, not the price at which you are selling. But if you, for example, and that's why the intersection is beyond, let's say, 12,000. So you have to produce 12,000, demand should be more than 12,000. Then only conventional thing will be more profitable. Otherwise, your additive manufacturing, if you produce, for example, one hard bulb, or one femur joint, or one gear of a very specific design, For conventional manufacturing, that's a very huge investment. For additive manufacturing, it's no cost at all. That's the advantage. Similarly, if you know do the tailorability, like I was saying, that you want to adapt to a particular design, change the according to thickness, along the thickness or the dimension, a lot easier here.
One thing.
Yes, sir.
About the rotation of the red line, it can go up because if the time taken is too much, and time is money, so therefore I can show that line is very low and very convenient. But actually, if that line is very high up.
No, actually, sir, you're right. For example, additive manufacturing cannot compete with extrusion components made by extrusion of polymers. I mean, that's so cheap and stamping. Like you do 1/3 and then you have a component. It's a very slow process. Unlike people tend to believe laser is so fast, but actually this process you basically look at a volume and divide that by 1 million or 1 billion droplets. You're creating one by one.
What I am going to suggest that how you can consider the time element, because in industry time is equivalent to money.
It's done by some marketing people, huh?
Okay, obviously. Thank you.
Sir, I have a doubt.
Yeah.
Sir,
Oh, right here, okay.
yes, sir. Sir, in Inconel 718, IN 718, which we use for the space researchers, mostly the superalloys. So you have made a layer of silicon or aluminum, the silicon layer. What kind of bond does it make with the austenitic alloy? Because the austenitic alloy which we are using will withstand till 1200 or 1300 temperature.
It's an FCC, whereas the other one is diamond cubic. So how do they talk to each other? That's
yes,
the question, yeah. So the trick is, I said silicon added. I didn't say silicon clad. So I'm adding some percentage of silicon so that I'm following a phase diagram and then stopping somewhere. And by stopping, what I mean is that it will give me the desired volume fraction of that silicate phase which I want. So I have to select my parameters such a way that my composition will give me exactly X volume percent of silicides dispersed in austenitic matrix, which is 0718. But I wouldn't do that often with superalloy because the advantage of superalloy is elsewhere, its own crib properties, right? So this is only when I'm interested in improving the oxidation resistance. So if I have, by the way, that example I showed was on titanium, not on superalloy. So on titanium alloy, which is in the not the combustion but the compressor part, there you reach, let's say 500, not even 350, 400 degrees centigrade. So if I can push more air, then the frictional forces will be larger, frictional heat generation will be larger. So I need a thin layer of silicides there, which can take me to 650 degrees centigrade. So it's only the thin layer where I have silicides dispersed, not a monolithic layer.
So because titanium alloys cannot withstand, basically Titan 31 or titanium alloys cannot withstand more than 500.
I mean, typically in compressor part, the highest temperature is about 350 to 400 degrees centigrade. That was to demonstrate that with the same alloy base substrate, I can improve the oxidation resistance. That means it can withstand. There's no melting. Basically, it's oxidation, which titanium is highly, has high affinity for oxygen. So in order to prevent that, you create a barrier layer. See, for oxidation, always remember, cations have to go up and anions have to come up. So in between, you create a barrier layer with this silicide. So they don't talk to each other. So oxidation stops.
Thank you, sir.
I have a question. One of the observations in this area is that more than 90% patents in additive manufacturing are owned by corporations or industries. And almost 100% publications are from academics and laboratories. So these compartmentalization, how do you look at it?
No, it's not true, particularly in countries like US and France. There, the patents are filed both people from academia and industry. Similarly, many of the spun-off companies actually are spun off from big national labs in the US. Many of them.
Yeah, at least in USA, this is the trend.
Yeah. In India, it's happening. Like Skyroot is one example. There are others. Maybe Naga can know a little more. So there are, well, we wish always more, but that's not happening, yeah. There's a gap.
Thank you.
He had a question.
Sir, thank you for a very nice presentation. Sir, I seek some information. You are, sir, talking regarding this turbines and all these things. So I have a specific application that is turbocharger.
Turbo generator?
Turbocharger.
Charger, okay.
So that is basically utilized in ships and some aeroplanes and railways, and that is for all these things. So thing is that because it is working in a very different conditions, so it is corroding and it is failing frequently, and due to that. So is there any method to improve the surface properties or something like that?
I would just first ask, what's the section thickness of your propellers?
So, that will vary from place to place as far as the application is concerned.
If it is over a millimeter,
It is more than a millimeter.
then this kind of a cladding methods can very well be applied. If it's less than a millimeter, then during the processing itself, we may end up damaging more than creating a new layer. So if it's a few millimeters, we can always have a very thin layer. Like I was saying, that your problem in turbocharger would be coming from erosion, high temperature oxidation, and corrosion, erosion both. So I have to create a barrier layer. So on a millimeter, I can always think of creating a few tens of micrometer layer, which can prevent this. So if you can give me some coupon, I may not do it for a charger. If you give me some coupons, flat coupons, I can always try them.
Yes, sir, I'll try my best.
Thank you.
Thank you, sir. Thank you. And it was a truly applied part of metallurgy. We were able to get an insight into the various characteristics of oxides. Sir shared his lab work in laser cladding, additive manufacturing, welding in the field of superalloys, stainless steels, titanium, and so on and so forth, and complemented with various characterizations starting from microstructures and tribology and many things. Thank you, sir. I request Professor Amitabh Ghosh to felicitate sir on behalf of our institute. Yes, a small token of appreciation from our institute to sir.
He was my director.
Thank you, sir, for joining us. Big round of applause. A token to keep a memory from us. Thank you, sir. Thank you. No. Sir is saying no to introduce, but I want my students to know to whom they are interacting with. So now the next lecture is from Dr. Naga Hanumeya. Sir is Director of Central Manufacturing Technology Institute, and he has rich years including micro, nanoscale manufacturing technologies, modular, reconfigurable machine tools, additive manufacturing, tool design, rapid tooling for injection molding, cost modeling, manufacturing process selection, and manufacturability evaluation. His team has developed 12 cutting-edge technologies, resulting in 5 successful technology transfers. He has for his role in shaping the Indian manufacturing policy in 2003. And there are many more accolades, but we are short of time. You can Google his profile very well. I request sir to start. Thank you.
morning, and this honor is also nervous to present before my established researcher and our mentors. My presentation is I'm not talking about the technical things because 20 years I worked in CSIR mostly as a bench researcher, working with students and publishing, patenting and all. But last 5 years I'm there as a director at CFTI, where CFTI is primarily focused on solving industrial problems. I tried, and since this focus is also on the translational research, I will try to cover what are the challenges in translation research and how to address,